Okay, so we're now moving into the parallel pipe problems. So parallel pipes, you should really just think of them, right? Like those parallel electrical circuits. It's the easiest way to get to a solution quickly. Where here's my delta V, right? Here's like a resistance 1, resistance 2, and the resistance 3. These are electrical circuits, right? And I have some I total moving because of the battery's potential energy. So this is exactly the same if I just were to replace these instead of resistors, right? We'll just call these things pipes. Draw them like that, right? Instead of a battery, right? Like this. Then you'll have a change in head. And instead of current, we'll have volumetric flow rate, and each of these has their own resistance. So just as you did in circuits, where the only thing you really know is that since this delivers this difference in energy, this has to be the exact same but opposite, but all these are exactly identical. So that's why for parallels, what we will say is really the exact same rules you had for circuits, where the total flow rate going in has to equal the total flow rate going in, and this could be up to n. And then the other thing that we know is that all of the head is exactly the same. Let's say this was actually total, right? Right? The potential difference here is exactly the same if it's there, exactly the same as there, and exactly the same as there. So that's the setup for these parallel pipe problems. But when it comes to actually solving these things, again, remember that our Ohm's law for pipes isn't that nice because I'll call it K, right? The Ohm's law for pipes has this squared in there. And in fact, worse, this, right, because this had friction factors in it, this is also a function of Q. So it's not exactly that easy to solve this. We can't use matrices to analytically get these values we're trying to get at, but you at least know what equations to set up based on these relationships. It's very fundamental, the idea that if you have parallel flow situations, that the flow rates have to at least add up to whatever the pump's putting out. There's nothing where that's the simplest kind of assumptions you can make on these types of systems. The only thing we don't have is that linear law that for electrical circuits we have. So if you had a bunch of complex electrical parallel circuits, you could write out a big matrix and then invert it, and you would get the solution of all, let's say, the Ks, or whatever it is you're trying to figure out. But it's different for pipes, and you should just appreciate the fact of how badly this messes things up. The fact that the flow rate is squared, and the fact that the resistance had those Darcy friction factors in it, right? You can think of this as this, where because there's a Reynolds in there, the Darcy friction factors are functions of flow rate as well. So your resistance is a function of flow rate, and the flow rate is even squared. So it's a nonlinear relationship for components, but that's the layout for these types of problems for parallel flows. So it's nice to point out what's harder and what's difficult for the parallel situation. For the parallel situation, right, finding the change in head is actually hard. This one's the hard problem, and that's because the way you have to solve this is you have to so you have to guess a list of these flow rates, and with the restriction that you at least need to have this must be true. So however you're guessing these, there's some distribution of the flow rate that at least needs to satisfy this, right? So so the idea of before, the easy way to do this for pipes in series, remember it was really easy to actually figure out what the head loss was. given all of the pipe dimensions, flow rates, and diameters, right? So again, we're in the exact same situation that we're given, right, all of the components, like we know the total flow rate, we know the dimensions, we know the materials, but, right, this is the same, right? And we're trying to find the head loss in a parallel system. So when they were all in series, this was easy because you just had to plug in things to a summation formula and then calculate what this is. But for the parallel problem, it's tricky because you actually have to guess how the flow rate that you know is distributed throughout the parallel things. And then it's fairly kind of simple because after you really make these guesses, right, then you can compute each, right, for each resistance, you could calculate all of the head losses based on the components, right? And then sort of the last step is you just then want you just check to see, make sure that all of the head losses are exactly the same. If they're not, you have to redo and iterate some updated formula, right? Because again, we're fine, right? Again, the idea is that right, we know what this Q total is, and these are resistances to flow. Close to 4, right? So this is easy to understand. You're just trying to figure out, well, to achieve this parallel flow situation, what pump do I need to buy? What's the energy needed? You have to, right? That's the idea of guessing then how it's distributed based on all these diameters, because each one of these pipes has, right, diameters. This itself could be a series problem alone, right? So it could have diameters involved, it has materials involved, and these make up the flow resistance for each of them. So you guess the flow rates going in parallel, you then compute for each of these, right? Each of these has a head loss that you can easily calculate because this itself is just a series problem. So, right, you know because you guessed it, the flow rate going in. Since you guessed it, right, you can just do that summation formula where you have let's say, I'll get summation formula, right? Squared. So this then is easy to calculate because you just need to then calculate it. And then you just need to check to see that all of these are the same. You need to ensure this is the same after you've done those processes. We can do a little more examples of how you actually do this, but that's what it is. And it's all hard because of how it's nonlinear when it comes to parallel flows.